this line of research, which researchers in Inria, so researchers in Inria in France, they developed a new theory called compressive machine learning. And basically, they try to generalize the theory of compressive sensing to the infinite dimensional spaces. For example, if y is your measurement in the classical sense of compressive sensing, and you want to recover x star, and you have, of course, a noise as well, then most of the time, in classical compressive sensing, you say x is a long vector, but in compressive machine learning in Inria, they try to develop a theory that x star is a probability density function. And, for example, a Gaussian mixture model could have an infinite length. So, for example, you could estimate a probability density function by sum of many normal Gaussian variables, but this sum could be from I to infinity. But k of the biggest of them are important, just like compressive sensing, k of them are more important than the other. So in restricted isometry matrices, so I was talking about restricted isometry property, or RIP, in the previous lecture. But here, if you project it and square it in L2 norm, you will see that it's between, so the distortion is delta, y minus delta x squared. And the key result is that m is of k log d by k. But designing deterministic matrices M that have restricted isometry property in polynomial time is still an open question. But modern popular choices include matrices where entries are ID Gaussian or Bernoulli variables. So, in random projection, you have many different ways to create your matrices. So we have, I say, this is in F domain, and this is in E domain. So these are semi-norms. I was talking about them. But the lower restricted isometry property, you just need to satisfy x minus x prime less than alpha m x minus x prime. This is lower restricted isometry property. And let me define what is IOP, which is instance optimal decoder. So we want to go from space E to space F. We want to project it by a matrix M, and so the decoder is just the opposite. You go back to the original space. So we have some kind of manifold here. So this is your decoder, and this is your projection. So when I say that we have a decoder, IOP, instance optimal decoder, from M and MX star plus E to X tilde, it means that we are going to reverse back to the original space. So it satisfies IOP if decoding is stable to modeling error. So definition, A decoder satisfies IOP for the operator M and model theta with constant A and B, which are these constants are greater than 0. Of course we have a pseudometric. It's different than a metric. So you have a pseudometric DE such that the difference, your error is less than, so x star is something here. So you have some error when you go back to the original space, and you can get this measurement error by, we can bound it by somehow this one, plus B norm of E in the F space. So A and B are constant, which are greater than 0, and D of E, this pseudometric, is infimum of all point X, where X, your model can be, you can find the infimum of this over all distances. So there is a theorem by Bourier that says consider M and a model theta. So if there exists a decoder delta which satisfies that instance optimality property for M and theta with constant A and B greater than 0 and pseudometric DE that I've just defined, then the operator M satisfies the lower restricted isometry property. Also, the second part of the theorem of Bourier says if M satisfies L-RIP, then decoder delta M and Y is argmina of MX minus Y for the model. Satisfies so this delta satisfies IOP, and the pseudometric DE is, you can construct it like this. Of course, you don't know M. M is general. We haven't constructed that yet. But at least you can say something like that. I assume you know about delta covering balls, and so some necessary backgrounds. But I should define normalized secant set, which is at S of eta with respect to norm, which is equal to, it's like all the differences, but normalized differences, such that y prime is in y, and we say that it is the difference is greater than eta. So fix eta, for example, fix y, so y is fixed, okay? So you find all of these with a ball of great radius, it should be out of the ball of radius eta, and then the Pinsker inequality says that, these are some prerequisites to understand the theory, says that the total variation norm of the difference is less than 2d KL P1 P2. You can see the complete proof in a dissertation of researchers in Inria. They talk about sketches, and these theories is one of their latest results. So by symmetry, we can say that the total variation. So in the proof of the theorems, we use these facts, which is d of KL, which stands for Kullback-Leibler divergence between pi and pi 2, dKL of pi 2, so we make it symmetric. And they can bound the total variation by trace of sigma do minus 2 plus mu1 minus mu2 squared. So the important thing is just you can bound this total variation. So the distance between your points do not change too much. It is controlled by this term, by these terms. Sorry for saying these technical things because we need them. So a pair FR and alpha is a random feature expansion of the kernel if K of Z and Z prime is expectation of omega drawn from a probability distribution over a measurable space, and phi of omega Z and phi of omega Z prime. And the random feature are uniformly bounded by BFR less than infinity if supremum of phi omega Z is less than B of FR. So let's define some sketch. As you know, sketch is just could be seen as just a random projection going to the you know, some people call it embedding, sketch. All of them could be seen as a single entity. So if you have a multivariate function f z from phi to m-dimensional space, then you can define the norm of mu to be supremum over all inner products where f is in F. So psi mu of omega is the inner product of, so you know this is the characteristic function of mu. This is not important, but the inner product of mu and f is mu and f1, mu and fm, where fm is e to the minus j omega transpose x. And so this one is just f1 d mu, fm d mu. So using this notation, now I can say that the norm of mu k, you can define it by the characteristic function that's of defined, d lambda omega, and omega is your random. It's a randomness comes from here, and so. And also, you can define the FR norm to be supremum of these inner products. So this is just the L infinity, psi mu L infinity, and the sketching operator A mu. So the important thing is this is the sketching operator. So instead of traditional compressive sensing that you say, okay, this is x is a long vector, now mu is a probability density So it's an infinite dimensional object, not just a single finite dimensional vector. So we have generalized it to bigger spaces, bigger. So it's really a generalization of compressive sensing, and it's very nice that we can work with. We can do the same thing to find the probability density function in machine learning. So this one is equal to characteristic of omega 1 till characteristic of omega m. Again, omega is random. So this is, of course, we work with real numbers, but in general, because the characteristic is a complex number, so you write it as a complex number. So there is a lemma that says that, norm of k and norm of the L2 norm, both of them are less than FR norm, and it is bounded by BFR total variation norm of that mu. And now you can write decoder. So your decoder, which I say you go back, what is that thing, that point that minimizes AP minus y, the L2 norm. And the interesting fact is here. Because mu is a density function, probability density function, so it's like just finding the expectation. So this is exactly equivalent to, but because we have just m measurement, so I'm talking in the language of compressive sensing, but now your elements are just probability density function in an infinite dimensional space rather than just some finite dimensional vectors. So this one is expectation of, I said that omega is a random, so you draw it, and then omega is a random vector. But because you do the inner product with your vector, then it becomes just a scalar. And so psi mu of omega squared, this is equal to mu squared. So empirically, y hat is e to the j omega xi, and this is a p hat n. So if you say that mu is the difference of two probability density functions, then to prove that A satisfies the local RIP, so we want to say that this one is equivalent to this one. So the distortion, I always use the term distortion because all of the metric embedding, what matters at the end of the day is just your distortion. And information preservation guarantee is something that we need to show that the sketching operator satisfies the non-uniform LRIP, local RIP. So I mean, there exists alpha and eta such that for any p theta inside your model with high probability, you can say that p theta minus p prime theta is bounded by a p theta minus p prime theta for, of course, for any p prime in your model. And I should talk about a non-uniform version of normalized second set. And so